Have you ever wondered how your computer, with hundreds of things running at once, instantly knows which task is the most important? Well, today, we're going to pull back the curtain on the incredibly clever data structure that makes it all possible, the heap.
All right, here's what we've got on tap. We're going to start by outlining a really common problem. Then, I'll introduce the heap as the elegant solution. We'll see it in action, understand why it's so ridiculously fast, and finally, we'll look at where you can find heaps out in the real world.
Okay, so first things first. Let's set the stage with a challenge that pretty much every programmer runs into.
I mean, think about it. It's like an emergency room. New patients are always arriving, some with more critical needs than others. You constantly need to know who's next, who has the highest priority. It's the same for your computer's task manager. There's always a need to handle the most important thing first.
You know, if you try to solve this with a simple list, you get stuck. You have two kind of bad options. With an unsorted list, throwing a new item on is super fast, but finding the most important one means you have to look through everything. It's slow. On the other hand, if you keep the list sorted, finding the most important item is instant. It's right at the top, but adding a new item is a nightmare because you have to shift everything around to make room. We need something better.
And that something better is a truly beautiful data structure called a binary heap. It finds this perfect, happy medium between those two extremes.
So what is a heap, really? Well, at its heart, it's just a special kind of tree. And its specialness comes from following two very simple but very powerful rules.
And here they are. These two rules are everything. The first one, the Heap-Order Property, is basically an org chart for importance. The boss, the most important item, is always at the top, and their direct reports are always less important. The second rule, the complete binary tree property, just means we're efficient. We don't leave any gaps. We fill the tree up completely from left to right.
And here's what that looks like in the flesh. See that number at the very top, the 4? That's our most important item, right at the root where we can find it instantly. And notice the shape. Every level is packed, filled in from left to right, no holes. That's our two rules working together perfectly.
Okay, but things in the real world are always changing, right? A data structure is only useful if it can handle constant updates. So let's see how this elegant design actually works when we start adding and removing stuff.
All right, check this out. We've got our perfectly organized heap. Now let's say a super high priority task comes in. An emergency. We'll give it a priority of 2. Let's watch how the heap handles this new arrival.
So, first rule, we can't leave any gaps in the structure. So we just stick the new 2 in the very next open spot at the bottom. But, now our whole org chart is wrong. A 2 can't be working for a 6. Our heap order rule is totally broken.
No problem. We just have to let it find its proper place. We call this bubbling up. We compare the 2 to its parent, the 6. Since 2 is more important, they swap positions. It's already climbing the ladder.
But we're not done. We check again. Is 2 more important than its new boss 4? Yep. So they swap one more time, and boom, done. The heap is valid again, and our new most important item is sitting right at the top. Simple.
Okay, so adding an item makes sense. But what happens when we finish that top priority task? We just pluck it off the top, but that leaves a big, empty office at the CEO level. To keep our structure intact, we do something that seems kind of weird at first. We take the very last employee in the company, the item at the very end, and we promote them all the way to the top.
Of course, that totally messes up the order. A 13 has no business being the most important item. So this time, we do the opposite of what we did before. We let it bubble down. We look at its children, find the smallest one, in this case, 5, and we swap them. It's still not in the right place, so we just do it again. We compare it to its new children, find the smaller one, which is 11, and we perform another swap. And there we go. It finally finds a home where it fits into the hierarchy. And just like that, with only a few simple moves, the entire heap is perfectly balanced and ordered once again.
Okay, that might seem like a lot of shuffling around, bubbling up and down. So why do we bother with all this? Well, it all comes down to one thing: unbelievable speed.
Here is the real magic trick. Because this tree is always kept perfectly balanced, it never gets very tall. Its height grows logarithmically, and what that means in plain English is, well, it's mind-blowing. If you have 1,000,000 items in your heap and then you double it to 2,000,000, the number of swaps you need to do only increases by 1. That's it. It is incredibly, incredibly efficient.
So let's look at the final scorecard. Finding the most important item? Instant. It's always right there at the top. Adding a new one or removing the top one? That's our super fast logarithmic time. You compare that to our simple list from before, it's not even a contest. The heap wins hands down.
Now, I know what you might be thinking. This looks kind of complicated, with all these tree nodes and pointers and connections. But the way this is actually built under the hood, honestly, it's probably the most elegant part of the whole thing.
Get this, that entire tree structure you just saw, it's not actually a tree in memory. It's just a simple list, an array. It uses some clever but simple math to pretend it's a tree, figuring out who the parent and children are on the fly. No pointers, no complex objects, just a list. It's brilliant.
And the chances are you've used this exact thing without even realizing it. If you've ever worked in a language like Python, its built-in module for priority queues is called heapq, and it does exactly this. Heap push and heap pop are just fancy names for the add and remove operations we just walked through working on a plain old list.
So what's the big takeaway here? It's this. Sometimes, the hardest problems don't need more raw computing power to solve them. They just need a smarter, more elegant way to organize the data. It really makes you wonder, doesn't it? What other huge challenges are out there just waiting for the right data structure to come along and make them simple?